Okay, we're going to try a significance test for a proportion now. Turn to section 9.2 and try out number 41. Um, Pause me now and give it a go. All right, so as you were reading through the problem, I hope you took some notes along the way. Um, we have P equal to 0.37. That was the previous proportion of people satisfied. You should have underlined the fact that we had an SRS telling us it's a random sample. We have a sample size now of 200. The 2,500 was telling us that there are more than that many students at the school altogether. That's our population size, capital N, and we just know that it's more than 2,500, somewhere around that. We know that our number of successes, the people who are now satisfied, X, is 83, and we're doing a test at the significance level of 5%. Another good set of phrases to underline are where it's asking if the change was effective, and effectiveness was defined earlier in the problem as improving satisfaction. So those are also kind of important things to pay attention to as you're reading through. All right, so we're ready to get going then. First, you're going to define your parameter. Keep in mind that the information you're getting from each person could be categorized as yes or no, success is failure. So this is a proportions problem, even if I hadn't told you that at the beginning. So let P equal the true proportion of students who are now satisfied with the parking situation. Because this is a significance test for a proportion, we use a one proportion Z test. Be careful not to abbreviate that when you're showing your work. You don't want to say one prop Z test, even though that's what we do on the calculator, because calculator speak is not formal statistical language. Okay, so now we want to set up our hypotheses. Remember, your hypotheses should be about the parameter, and the parameter in question, the previous value was 0.37. We're looking to see now if it's improved, so we're looking to see whether satisfaction has increased, so is now greater than 0.37. That greater than came from the phrase improve or was effective, saying that satisfaction has gone up. All right, now conditions. Random. We know it was a random sample because of the SRS. Remember, it's not enough to just put a check mark next to your condition. You have to explain why it's true or how you know. Independent, the 10% condition, so 10 times n, 10 times 200 is 2,000, and we know that we have more than that many students at the school because we're told that it's more than 2,500. So there are more than 2,500 students at the school. So the 10% condition is satisfied. Whoops, not 110. Normality. Be careful, a lot of people get so enamored of the central limit theorem that they try to use it for proportions, but central limit theorem is just for means. So even though we have a very large sample, we need to check that n times p greater than or equal to 10 and n times 1 minus p greater than or equal to 10 condition. Remember that this is, in interpretation-wise, this is saying expected number of successes, that's n times p, sample size times probability of success, and expected number of failures, based on the null hypothesis. So it's not a bad idea to put the little null sign in there to remind yourself that you're using the null hypothesis value, not the actual number of successes from our sample. So we have 200 times 0.37, which is 74. That's bigger than 10. And then we have 200 times 1 minus 37% is 63%. That's our probability of getting an unsatisfied customer if the null hypothesis is true. So that's 126, which is also bigger than 10. And so now you want a little concluding sentence explaining what you just found. The expected number of successes and failures, or expected numbers, I guess, are each at least 10. So we've met that condition as well. So all of our conditions are met, and we can proceed to calculations. Now you always need, for a significance test, you want to get a test statistic. In this case it's a z-test, so that's a z-statistic, and you want to get a p-value. Degrees of freedom are just for t, and so we don't use that for z. So our test statistic z, remember this is like a z-score. It's our sample value, our statistic, so that's p hat, minus our null hypothesis value over the standard deviation based on the null hypothesis. That guy. Okay, so in this case I recommend going to your calculator. Choose from your test menu the one prop z-test, number 5. Enter in your null hypothesis value, number of successes, sample size, choose the correct alternative, and go to calculate. This can tell you, you can see that p hat is 0.415, you've got your z-score and your p-value given there as well. So now we're going to copy down the key information here. 0.415 was our sample statistic. 0.37 is our null hypothesis value. 0.37, 0.63, 200. You don't even really need to calculate out this standard deviation of the sampling distribution because we don't really need that in itself. We can just give the z-statistic 1.32. And then what this means is that whatever our normal distribution is for z, so if we give it in z-scores instead of data, that's 0. Sorry, mine's a little tilted. Here's 1 standard deviation away, again about halfway down. 2 standard deviations away, etc. We're at 1.32 standard deviations away. Remember, z is a z-score, number of standard deviations away from the mean. And so our p-value is the area of that tail. The p-value, we're told from the calculator, is 0.0937. That makes sense with that diagram. Then in conclusion, since our p-value of 0.0937 is greater than alpha, which is 0.05. Remember, we always compare the p-value to alpha. Because it's greater, we fail to reject the null. So that means this is not convincing evidence that our alternative is true. The null hypothesis could still be true. So unlike the principal's claim, this is not convincing evidence that the parking change improved student satisfaction. All right, and that's a significance test for a proportion.